Hello and welcome to this today's session of our course on computational methods. So, before I go to the matrices which I am going to describe today, let us summarize what we did in the last two lectures. What we did in the last two lectures, we listed a large number of numerical methods which we want to study in this course, and in particular we discussed interpolation. And before we discuss interpolation, we distinguish between interpolation and curve fitting. Curve fitting also we will take up in a later lecture. And in interpolation, we described two methods. One was Newton's method of interpolation, in which we took divided differences between the values of the function. Given a values of x from x 0 to x n, the functions are defined at x naught, x 1, x 2 up to x n. So, you have f x naught, f x 1, f x n. So, the differences between the functions are your divided differences. So, using those divided differences we interpolate. So, that was the method for Newton's interpolation. Then Lagrange's method took the products of functions x minus x 1, x minus x 2, x k minus x n. So, these two methods we compared, we discussed the programs for both the methods, and we also said that whenever you interpolate for 4 data points using a third order polynomial, the polynomial is always unique. It is a unique interpolating polynomial whichever method you use. So, before we conclude this section, we also want to know what is the error in our interpolating polynomial. So, that is what is given here. So, look at this Newton's interpolating polynomial. So, P n x is given a sum of delta n f x naught. So, that is the nth order forward difference divided by n factorial into h to the n product of x minus x I. The summation is over all the forward differences delta 1, delta 2 all the way up to delta n. So, that is my sigma going from n equal to 0 up to n, and the product is from 0 to n minus 1. So, there are n minus 1 factors here. So, once I have this polynomial which is evaluated at each value of x, I would like to know what is the error in the interpolation. So, how do we define an error? The error in the nth order polynomial would be actual value of the function minus the interpolated value. So, P n x is the interpolated value, f x is the true value. Okay. So, that difference is given in terms of a Taylor expansion. We will consider that at a later stage. So, that difference is the n plus first derivative of the function. I have this function n plus first derivative at some value of xi, okay, multiplied by all these products divided by n plus 1 factorial, and the product is from 0 to n, that is x minus x 0, x minus x 1 all the way up to x minus x n. These are the products divided by n plus 1 factorial, and the derivative of the function at a value of xi. This value of xi is somewhere between x 0 and x n. So, such analysis allows us to find out what are the errors in our method, and this is very important. We may not refer to it again and again, but there are always ways of estimating the errors in our numerical methods, and that is going to be important. So, we will conclude this section on interpolation now, and now I shall go to the method on matrices. We will be considering matrices now, that is my next task. I shall go to that. So, I will be considering all the operation on matrices. Okay. So, now let us ask this question, how do these matrices arise? So, these matrix operations arise the first time when we study linear equation, linear simultaneous equations. Suppose I have variables x 1, x 2, x 3 up to x n. I have these n variables x 1 to x n, and I want to get the solutions to such equations. Okay. So, the first equation is a 1 1 x 1, a 1 2 x 2, a 1 3 x 3 up to a 1 n x n. This is my first equation between the n values of x. So, the second equation is a 2 1 x 1, a 2 2 x 2, a 2 3 x 3 all the way up to a 2 n x n. So, the first equation is equal to y n y 1, the second equation is equal to y 2. So, the last equation an1 x1 plus an2 x2 plus an3 x3 and the last term is ann xn is equal to yn. So, I have my right side is y1 to yn and my left side there are n equations and there are n equations for n unknowns. What are my unknowns? x1, x2, x3 up to xn. So, there are n unknowns. Only if I have n equations, then I have a unique solution. For example, suppose you have a simultaneous equation for two variables x and y. If I have variables x and y and if I have two equations for this x and y, then only I can solve it, because if there is only one equation between x and y, then I do not know the values of x and y independently. At best, I can express x in terms of y. For example, a x plus b y equal to 0, this is an equation. So, my a x will be equal to minus b y and x will be minus b by a into y. So, I have solved x in terms of y, I have no independent answer for x, because I had only one equation between x and y. So, if I have two equations between x and y, I can solve it uniquely. So, this is an example which generalizes that equation for x and y into equation for x1 to xn. So, there are n equations, n unknowns and n values of this y1 to yn. So, one way to solve it would be to represent this whole thing as a matrix equation. So, what is a matrix equation? My right side y, I write it as a column vector, y1, y2, yn, I write it as a column vector, that is my y. Left side is a column vector x. So, what is this column vector? x1, x2, x3, x4 up to xn, this is my column vector x. Now, A is a matrix which multiplies a column vector x and gets a product y. So, A x gives me y. Okay. So, what is A now? This is an n by n matrix. These are my values for that n by n matrix, A11, A12, A1n. This is my first row and this is my second row and this is my n row. So, this is an n by n matrix. So, when I solve this equation A x is equal to y, I can get a solution provided I can get an inverse of the matrix. Okay. I shall define an inverse shortly. All I have done, A into x is equal to y. So, suppose on the left side I multiply by A inverse. A inverse into A is 1. So, x will be A inverse y. Okay. So, this is how I write the solution for this. Okay. So, to solve for this equation, I need to find out what is A inverse. Okay. So, actually this should be x inverse, sorry, x should be A inverse y. This is a mistake here. It is not y is not equal to A inverse x, actually y is equal to A x. You see that y equals A x. So, if I want x, I should take A inverse on the left side, A inverse into A will be A inverse into y. So, please read this as A inverse into y will be x. I am solving for x. Okay. So, what is the main requirement here? I need to get A inverse, and to find A inverse I need to have a determinant, because only if I have a non-zero value of the determinant, then I can get A inverse. So, that is what is shown in the next slide. So, let us go to the next slide. So, before I go to this, let us define A inverse now. A was already defined in the last slide. What was A? It is an n by n matrix, A11, A12, A1n, this is my first row, A21 up to A2n is my second row. So, I have this matrix A. If I can get its inverse and the product of this is my identity matrix. What is an identity matrix? All the diagonal values are equal to 1 and all off diagonal values are equal to 0. That is my identity matrix. And what is the property of an identity matrix? Multiply any matrix by an identity matrix, I get the original matrix. And the other thing, so this particular multiplication A inverse into A gives me I, and also A into A inverse also gives me I. So, whether I multiply A inverse on the left of A or on the right of A, I get the same result. This is true only for this multiplication, and in general matrix multiplication is not commutative. What is the meaning of that? A B, the product of two matrices A and B is not equal to B into A. So, verify this taking any two simple 2 by 2 matrices. Take 2 by 2 matrices and in general they will not commute, that is the product depends on the order of multiplication. But if one of the matrices is I, then there is no problem, because the identity matrix commutes with all the matrices. So, what is my next task? My next task is to define the elements of this A inverse. So, A inverse is the inverse of matrix A. Now, I want to define the elements of A inverse. So, this is the formal definition of the inverse of this matrix. So, ijth element of the inverse. So, A inverse is the inverse of matrix A. Ijth inverse is given by the cofactor of element Aj divided by the determinant of A. So, to determine the ijth element, I need to determine the cofactor of element Aj. So, before I go to the cofactor of the element Aj, let me generally define what is a cofactor. So, cofactor of A32. So, what is A32? The third row and the second column of this matrix. A32 is the element which is the third row and second column. So, the cofactor of this particular element, each element will have its cofactor, that is given by the determinant of a matrix, which is obtained by deleting that row and that particular row and that column. So, if I want cofactor of A32, I delete the third row, I delete the second column, and I get the determinant of the lower order matrix. So, this particular matrix will be one order less than this, because if A was a 4 by 4 matrix, the determinant corresponding to the cofactor will be a 3 by 3 matrix. So, determinant of this matrix multiplied by minus 1 to the I plus j. So, what is I plus j? I was equal to 3 and j was equal to 2. So, I multiply minus 1 to the power of I plus j. What is the meaning of that? Whenever I plus j is odd, there will be a minus sign associated with the determinant, and whenever I plus j is even, there will be a plus sign. So, what will be a cofactor of A11? For A11, I delete the first row and the first column. It will be determinant formed by the remaining values 3 by 3 matrix starting with A22, A23, A24 all the way up to A42, A43, A44. I get the determinant of this and multiply by minus 1 to the I plus j. I plus j was 1 and 1 here. So, there will be a plus sign. So, whenever I get a cofactor of A11, A22, A33, A44, always the sign is going to be positive, because when both I and j are equal, I plus j is always even. So, the cofactor of all the diagonal elements will have a plus sign here, and of course, you remove the appropriate row and column to get the cofactor. So, that is how I define the element of my inverse matrix. So, when you get the ijth element of the inverse matrix, note carefully. So, I need the cofactor of element Aj. So, if it is ijth element, I need the cofactor of jith element and divide by determinant A. So, since I have defined the element of the inverse, I also need to now define a determinant. So, you know the determinant of a 2 by 2 matrix, let us say A, B, C, D will be AC minus BD, it is known, it is a simple 2 by 2 case, it is 2 terms. So, when I have a large number of rows and columns, so my determinant A for a larger than 2 by 2 matrix will be given by this definition. This is my definition of the determinant. What is this definition? Sum going from 1 to n, k is going from 1 to n, aik, cik. So, there is, I take ith row for example. If I take the ith row, so let us say I is equal to 3. So, that will be A31 into C31, A32 into C32, A33 into C33 and A34 into C34. So, to expand this determinant, I can expand from any row or any column. In this case, I gave this example of expanding from the third row. Instead of third row, I can also expand from the first row. So, when I expand from the first row, A11 into cofactor of A11. Cofactor of A11 will be this particular matrix whose determinant I take. So, a determinant can be expanded by any row and any column. So, I will get the same value for the determinant regardless of how I do. So, what have we done in this particular slide? We have given a definition of the determinant and we have given a definition of the elements of the inverse matrix. Now, we go ahead and outline a procedure how I get the determinant as well as the inverse of a given matrix. So, before I proceed further, suppose you want to find the determinant by multiplying all these quantities. So, for a 2 by 2 matrix, the determinant consists of only 2 terms. For a 3 by 3 matrix, it will have 3 factorial terms. So, for an n by m, there will be n factorial terms which I want to calculate all the n factorial terms, then add them to get the determinant. And you know, as n becomes large, n factorial becomes very, very large. For example, try to calculate what is 13 factorial. So, I need 13 factorial terms to calculate a 13 by 13 determinant. And my assessment is that if you want to calculate 13 by 13 determinant by hand calculation without using a computer, using this method, even your whole lifetime may not be sufficient. To convince yourself that this is right, calculate the time you will require to calculate say a 6 by 6 determinant by hand. Okay. So, now I shall go to the next slide, which gives me the procedure to obtain this inverse of this matrix. So, what procedure I am going to use? The procedure I am going to use is that once I have a matrix like A, I will convert this matrix by multiplying several matrices on the left, so that the diagonal elements are converted to 1 and the off diagonal elements are converted to 0. So, I am going to multiply by various matrices onto this matrix A from the left side and convert this matrix into an identity matrix, and let us see what are those 3 particular operations. These I call elementary operations. There are 3 elementary operations. We will illustrate with examples for all these 3 operations. So, first operation in EIC. So, what does this operation do? It multiplies the ith row of any matrix by constant C. So, I want to multiply the ith row of any matrix by constant C. How will I do that? I take an identity matrix and the ith row and ith column of this identity matrix is multiplied by C. So, it is the diagonal value. No, identity matrix has only diagonal values. So, if I take the diagonal value of the ith row and ith column into C of the identity matrix and multiply a given matrix by this EIC, I will have a situation where the ith row of this given matrix is multiplied by C. So, that we will take in the example in the next slide. So, this is my first elementary operation. What does it do? It multiplies the ith row of a given matrix by constant C. The second elementary operation is, suppose I want to exchange rows I and k of a given matrix. I want to exchange I and row. So, to exchange I and row, what I do? I go to the identity matrix, exchange I and k of this identity matrix and then multiply by this exchange identity matrix onto my original matrix. So, this is my second operation, exchanging elements of a given matrix. So, the third operation is called EIKC. What is this third operation? Replace the ith row of a given matrix by ith row plus C times kth row. Remember, I have ith row and I take C times kth row. So, when I do that, what will happen to my original matrix? I have row I of the original matrix, which is replaced by row I plus C times row k. So, to do that, I take the identity matrix, okay, replace the identity matrix itself by I times the C times row k is added to row I. I will give you examples. So, let us now consider the example here. What is EIC? So, I have the identity matrix, the ith row of the identity matrix is multiplied by C. So, all these other elements are 0. So, only the diagonal element of matrix C is multiplied, diagonal element of this matrix is replaced by C in place of 1. So, if I take this matrix and multiply to a given matrix, verify yourself that you will get C times the original matrix. So, that is shown here, okay. That you verify yourselves, and the question I will ask you is, instead of trying to convert the Cth row of a matrix by C times that row, suppose I want to change the cth column of that matrix. Suppose I have a matrix A and the entire column of that matrix I want to multiply by C times that particular column. Just think about how you go about getting this particular result. So, what I will show on the next slide now. So, this is my, what have I done here? I have taken the identity matrix. In the identity matrix, I have multiplied C times the third row. This is my third row in the identity matrix. Suppose for this I multiply by C. So, I will have 0 0 C. So, that I have added to the first row, that is C times the third row is added to the first row. This is for the identity matrix. So, with such a matrix I am multiplying my original matrix A11, A12, A13. So, what will happen when I multiply? This is my result. What is my matrix multiplication? The first term will be the first row of this matrix multiplying the first column of this matrix. So, what is that? 1 into A11 plus 0 into A21 plus C into A31. So, that is my first value of the product, that is what is written here, A11 plus C times A31. So, that is the first row and first column. What is the second row and column? 1 into A12, that is what is given here, that is A12 plus 0 into A22 which is 0 plus C into A32. So, A12 into C times A32. What is the third element? 1 into A13 plus 0 into A23 plus C into A33. So, the first row of this particular product now is A11 plus C times A31 plus A12 plus C times A32 plus A13 plus C times A33. All the other two elements will remain unchanged, because see the second one now. When I multiply this particular 0 1 0 to this second particular column, what will I have? 0 plus A21 plus A31. So, my second row and first column of this second of this matrix A prime is A21. Similarly, the next one will be A22, the next one will be A23. So, the second row remains unchanged, the third row remains unchanged. So, what I have done by this is called an elementary matrix. There are 3 elementary matrices. So, this is the most difficult one. I have shown you that if I multiply E13 times C and multiply on the left side of A, what I get is the first row of A changed to its original first row plus C times the third row, C times the third row, that is A13, E of 13 of C into A. So, this is how I can manipulate my original matrix and get my results of choice. So, now let me summarize this Gauss algorithm. So, before I summarize, I think I should take one example. Okay, I think it is all right. I shall just summarize my algorithm, because we will have to use this algorithm throughout our program. So, what is my Gauss elimination algorithm? Whenever I have a matrix, suppose I have element AKK. So, what I want to do? I want to normalize that element AKK by multiplying the kth row by 1 by AKK. So, what will happen when I multiply the kth row by 1 by AKK? The diagonal element will become 1, that is my normalization, and it may so happen that this AKK is 0. So, if AKK is 0, I cannot divide by 0. So, what I do in that case? I exchange kth row by some other row, such that I replace my kth row by another row who has the maximum element in that particular row. So, such that I max will be of course greater than k. So, I exchange 2 rows if that AKK is 0. So, first part is normalizing that particular row, kth row. Then the second will be the off diagonal elements of column k. So, the diagonal element I have made it 1. All the non diagonal elements, off diagonal elements, I convert them into 0 by replacing the ith row by combination of row I and k. So, I take combination of row I and k to 0 all the off diagonal elements. So, now these 2 steps I shall describe. So, what will I do now? In my remaining slides, the superscripts k, k minus 1 etc. will indicate the stages or steps in the inversion process, and whatever operations I do on matrix A, I shall also perform those operations on matrix B. And what is my matrix B? It is equal to identity matrix in the first stage, and in the remaining stages it will go on including all the results of operations which are done on the left side. So, now let us take an example how to use this Gauss elimination algorithm. So, this is my Gauss elimination algorithm. Whatever I said in words is given here. I shall come back to this algorithm after I take an example. So, let me take an example and come back to this procedure. Okay. So, in my numerical example, okay, what I have done is I have taken a matrix A. The matrix A in this case is 4, 8, 2, 1. This is my first row. Second row is 1, 5, 3, 8, and the third row is 2, 7, 1, 4. And the last row 3, 8, 2, 1. My matrix B is an identity matrix. This is my starting point for matrix B. This is my original matrix. So, now I want to do all the operations on matrix A and B, so that I get a identity matrix. So, what is the first task? The first task will be I divide the first row by 4. So, this is my first row. I shall divide every element of this row by 4. So, what will I get? 4 by 4 is 1, 8 by 4 is 2, 2 by 4 is half, and 1 by 4 is 1/4. The same thing I will do for this. So, when I divide this by 4, I will get 1 by 4, 0, 0, 0. So, first I shall convert the diagonal element into 1 and all the off diagonal element into 0. Then the next time I want to 0 these off diagonal elements 1, 2 and 3. How will I do that? I take the new first row and take suitable combinations of this new first row and add it to the second row. And how will I do that? I will do all this by elementary operations. So, what we will do? We will conclude this lecture now. In the second lecture, I shall again begin at the same point and convert the matrix A into its diagonal form. So, I shall conclude the present lecture here, and in the next one I shall continue exactly where I left at this point. Thank you.